variants of LWE with it.
Great. So thanks, Daniel, for the introduction, and thanks to the organizers for inviting me. So I'm going to tell you about a recent line of work on exploring systematically new lattice assumptions and what they can enable for us. So since this talk is about new lattice assumptions, I'm going to start by recalling the classic lattice assumptions that we've come to know and love. So for instance, the short integer solutions, or SIS problem, says the following. Given a random matrix A, find a low norm non-zero vector that happens to be in the kernel of A. Throughout this talk, you should think about the number of rows of A as n, which is the security parameter, and the number of columns as m, which will be n log q, where q is the modulus. The short integer solutions problem is a mini-crypt assumption, oftentimes considered to be a mini-crypt assumption. It gives us things like one-way functions, collision-resistant hash functions, and digital signatures. Then we have the learning with errors problem, or LWE, a dual version of short integer solutions, which says that a random linear combination, a noisy linear combination, of the rows of this matrix A is actually pseudo-random. So here, the coefficients of the linear combination are the components of S, and then we're going to add a small amount of Gaussian error to each of the columns. So the learning with errors assumption has been a very versatile assumption when it comes to realizing a variety of cryptographic primitives. So in original work, when Regev first introduced it, he showed how to build public key encryption from learning with errors. Shortly thereafter, Gentry, Pikert, and Vankuthanathan showed how to realize identity-based encryption. Not long after that, Gentry and Brokersky and Vankuthanathan showed how to realize fully homomorphic encryption from LWE, technically from circular secure LWE. And this, in some sense, really put lattices on the board in the sense that it was the first time that lattice-based cryptography really realized something that was essentially out of reach from previous number theoretic or group-based approaches. And in the ensuing 15 years 15 years or so, since the development of fully homomorphic encryption, the community, including by many people in this room, have actually shown how they leverage the structure of integer lattices to realize a very broad range of cryptographic objects, including advanced encryption schemes like attribute-based encryption and predicate encryption, proof systems like snarks for P and non-interactive zero knowledge, as well as forms of obfuscation such as lockable or compute and compare obfuscation. At the same time, in spite of all of the success that Lattices has enjoyed in realizing advanced cryptographic capabilities, there do still exist several notable objects that are not represented on this list. These include even low-end objects that we might consider, such as broadcast encryption, and of course, the more high-end primitives that we heard about in Hotek's talk, witness encryption and indistinguishability obfuscation. And I should also point out that this is not not for lack of trying. In fact, the community has been trying for many, many years of trying to realize these cryptographic primitives from lattice-based assumptions. However, most of these schemes that have been considered here either did not have a concrete hardness assumption, they're sort of heuristic constructions using the structure of lattices, or they were based on a new lattice assumption that unfortunately was subsequently broken due to cryptanalysis. Question? And I should mention here that even if the assumptions underlying these schemes are broken, most of these schemes themselves do not have any attacks. So most of these schemes are still perfectly valid heuristic constructions of the corresponding primitive from lattice-based techniques. And in fact, there's a lot of recent developments. We heard about some from Hotek's talk this morning. So for instance, we have new constructions of broadcast encryption from the public coin-evasive LWE assumption, which is there are no known attacks. We have constructions of witness encryption based on a private coin-evasive LWE. And we also have many new indistinguishability obfuscation candidates by new lattice assumptions. And it's actually very exciting because this very afternoon, we'll actually hear about 3 of these new developments. So we'll be able to see what kinds of new lattice assumptions we are proposing as a community for realizing these high-end cryptographic objects. So in this talk, I'm going to focus on one particular family of assumptions called the Succinct LWE family of assumptions. And sort of the driving force behind this sort of overall research direction or research vision is we want to systematically explore lattice assumptions with minimal additional structure for some notion of minimality that will allow us to reason about the security of the simple and the most natural constructions of these cryptographic primitives. So we want to be able to find a simple assumption that allows us to justify the security of very simple and direct approaches for constructing notions like broadcast encryption and more. And the hope is that over time, we will ultimately be able to reduce the security of these primitives from standard lattice assumptions. And the reason that I'm actually very optimistic about this view is that we consider what happened in the domain of pairing-based cryptography. We saw a similar kind of trajectory. In the early 2000s, when pairings first came onto the scene, it enabled a very broad range of new cryptographic capabilities. Notions like attribute-based encryption, predicate encryption, broadcast encryption, traitor tracing, all of them emerged by studying the structure of bilinear groups. And when we invented these new cryptographic objects, we oftentimes relied on new cryptographic assumptions over groups with bilinear maps. But over time, and especially since the 2010s, we've been able to leverage our newfound understanding of pairing-based cryptography and ultimately reduce the hardness of many of these primitives based on very simple and minimalistic assumptions, such as the K-ling assumption. And the hope is that this similar kind of paradigm will follow by sort of studying these simple lattice assumptions. So in this talk, I'm going to focus on one particular assumption, the succinct LWE assumption. And the way that I want to view succinct LWE is not as a single assumption, but really as a general framework for coming up with lattice assumptions that actually captures several recent assumptions of this flavor. So the general template that we're going to follow is I'm going to conjecture that the LWE, or the SIS assumption, holds with respect to some matrix A, even if I give out some hint related to the problem instance. The question is, what does this hint look like? And in this setting, the setting that I will be considering today, the hint will be a matrix D sub L, which I'll describe the structure very shortly, and then a trapdoor for this matrix. Okay? And the matrix D sub L will have the following form. It's going to take the matrix A here, and I'm going to consider a block diagonal matrix, just put A along a diagonal many times, and then I'm going to concatenate it to it vertical stacking of matrices W1 up to WL. If you want to think about the dimensions, you should think about A as being the same LWE dimensions as before, n by m, and each of these WIs is also n by m. So this part of the matrix is very wide. This part is very narrow. And when I say a random gadget trapdoor, what I mean is typically you can think about T as a random matrix with discrete Gaussian entries conditioned on D to L times T is equal to the gadget. So notice when I describe this assumption, I haven't told you what the distribution of A is. I haven't told you what the distribution of W is. That will actually be a parameterization of the assumption family. Okay? But this is the general template that we're going to look at. So is the assumption family clear? It's basically a conjecture that either SIS or LWE is hard with respect to this matrix A, given a trapdoor for something that looks like this.
So the trapdoor is not given to anybody, right?
No, the trapdoor is public, part of the assumption. Yep, so it's basically assuming that the assumption holds with respect to A, given this trapdoor for a related matrix.
So what is W?
Sorry?
What is W?
Good, next slide. Yes, but is the formulation clear?
So the attacker is given both A?
Yes.
Both W1, W2?
Yes, it's given A, it's given all of the W's, and it's also given T.
Okay.
Yep, and it needs to break LWE with respect to A, or SIS with respect to A. Okay, so let's look at, there's several instances of this type of assumption. So this is, again, another reprint of the assumption family. So the first instance of this assumption was introduced in a joint work with Hotek, where we introduced something called the basis augmented SIS assumption, or the basis assumption. This corresponds to an instance of the assumption where the matrix A is uniform random, and the WIs were actually structured. They were structured in the following sense. Each of them is obtained by applying a random linear transformation to the gadget matrix. So WI can be written as WI prime times G, where WI prime is a random square matrix. This gives one distribution of the WIs, and in this work we show that this structure is useful for realizing functional commitments. We can also consider a different version of the assumption, where both the matrix A and all of the WIs are uniform and independently random. This is oftentimes referred to as the succinct LWE assumption, introduced by Hotek last year. And this was also shown to give both functional commitments as well as attribute-based encryption with succinct ciphertexts. In fact, in this particular case, the WIs have less structure, so you can expect that the succinct LWE assumption is a weaker assumption than the basis assumption, and indeed, this is the case. So this is actually a weaker version of the assumption. But this is not the only kind of distributions that we can consider. And let me tell you about another distribution. We can consider the case where the matrix A itself is structured. So before, I said A was a uniform random matrix. But I can also consider a structured version of A, so for reasons that will become clear shortly. So imagine the following scenario. I sample all of the WIs uniformly at random. And then I'm going to sample Ri, R1 up to RL, to be square matrices with Gaussian coefficients, so low norm values. And now I'm going to define a very structured matrix A. This will be a very wide matrix. It has L squared blocks, where the blocks, let's say, are indexed by I and j. And the ijth block is obtained by taking Wi, multiplying by Rj. And whenever I equals j, I'm going to add the gadget matrix to it. Okay? So if you think about this, if I plug in this matrix here into this D sub L, you can actually write down a trapdoor for this matrix immediately. The trapdoor is basically has R on the bottom, and then it has basically blocks of the identity matrix depending on where you need things to cancel out. Right? The fact that you basically have the gadget whenever I equals j is exactly what allows you to build a trapdoor for this particular matrix. Okay? So this is an example of a setting where I've picked the A's in a way that, that there's a public trapdoor for the matrix D sub L. So in this case, what is the succinct LWE assumption say? Well, it says that LWE holds with respect to the matrix A given this public trapdoor, which in particular, it means that LWE holds that these LWE samples are actually pseudo-random. Okay, and in particular, this is exactly the decomposed LWE assumption introduced in the recent work of Abram, Malavolta, and Roy. Right? It's basically conjecturing that S times WIRJ plus the gadget matrix whenever I equals j is pseudo-random. Yeah?
But you could also just assume it holds given the WI. Are you giving the WI? Oh, you are giving.
Yeah, given WIs and all the RIs.
And then you're saying then you don't need to give T. T is just.
Yeah, T is public. Yep, T can be publicly derived from the WIs and the RIs.
I see.
Yep.
But again, you say that LWE holds with respect to that. So what about the secret or the noise, the secret vector S for LWE?
Oh, it's all the secret S is always uniform random. Error is always Gaussian, just like in plain LWE.
I see.
Yeah, we don't change the distribution there.
So the
Yes.
that's the information that relates to us. Right?
Yes. We have information about A. Yeah. So this is actually a very nice assumption. First, it does not refer to any trapdoors whatsoever. Right? If you think about the previous versions of succinct LWE or the basis assumption, there it was asking that the sum lattice assumption holds even given a trapdoor. Here, there is no trapdoor. This is purely.
So now you mean that there's no trapdoor because it's given to you from.
It's a public. There's a public trapdoor. Exactly. It's a publicly computable object. There's no additional trapdoor that you're given. Exactly. Good. And this assumption is actually very similar in spirit to a circular security type of assumption. In fact, if I consider the assumption where I don't have this term, if I just give you S times WI times RJ, this actually holds from plain LWE. This is the classic BLMR style construction. So essentially what this is saying is that when I equals J, S times G is masked by a pseudo-random object. We say that the argument is that this result is still pseudo-random. So this seems like a very natural, very nice assumption. And I think understanding this better, and the relationship to circular security is quite interesting. And so an open problem here is, can we hope to show the hardness of the decomposed LWE problem? Either from plain LWE, that would be wonderful. That would resolve that would give many constructions that we don't know how to do today from the plain LWE assumption. Or can we hope for something slightly weaker, which is, can we hope to show the hardness of this assumption from some worst case lattice problem? Okay. All right, so this is another version, or we can view the decomposed LWE assumption as, again, another instance of this general family where we have a specially chosen matrix A here, for which now the trapdoor becomes public. And in a work by Abram, Malavolta, and Roy, they show that this is actually an even weaker version of succinct LWE, namely succinct LWE implies the decomposed LWE assumption. Okay. Yeah?
Why is there, I can see why it would be used in applications, but is there a special reason that you only add G and you just map it to G? What if you map it to kind of like random matrices with public trapdoors?
You mapped random matrices. I think that should also suffice for applications.
For applications.
Yeah.
But would that be a better assumption?
Unclear what the advantage would be. Yeah, I would have to think about it. Mhm. Yeah.
So again, was that the dot part of the
Yes.
was that the dots?
I just mean that this matrix consists of L squared blocks, where each block is of the form Wi times Rj plus G whenever I equals J. Yeah, so the first block is W1R1 plus G, then it's W1 times R2, then W1 times R3, and so on.
So you're okay, all of them, but you're not given the WI and RI individually.
You are. You're also given Wi and Ri.
So those are public.
Yes, those are also public.
Okay. So
Yes.
RI, WI, and then all those.
Yes. So you should view that this is basically the public LWE matrix. It has this special structure.
So and what is the problem?
Basically, LWE with respect to this matrix. So distinguish S times A plus error from random.
Oh, okay.
Yeah, does it make sense? Other questions? Okay, great. So if you look at this progression, every year we have a new version of this assumption. Each of them is progressively weaker. So maybe 2026, we can hope to get this from plain LWE. Yeah, so that's our job for this summer. Then we'll get a lot of applications. All right, so before I talk about how we use succinct LWE or any assumption in this general family to build new cryptographic objects, let me say a little bit about hardness of this assumption. And for simplicity here, I'm just going to refer to the succinct LWE assumption where the A's and the WI's are all random. Right? This is the simplest description. And sort of we can consider two different axes for hardness when it comes to this assumption. First, we can consider what happens as we vary the width of the matrices WI. So when the WIs have constant width, this assumption is false. In particular, given a trapdoor for this matrix, you can basically compute low norm vectors in the kernel of A, which will break SIS or LWE with respect to A. On the other end of the spectrum, if the WIs were very, very wide, right, as wide as the number of blocks, right, it grows with L times n log Q, then by standard trapdoor extension techniques and lattices, this will follow from the plain LWE assumption, right? What happens in the middle? We don't really know. So that I think is something that would be interesting to understand better. And in particular, the applications I described will require instances of succinct LWE that hold when the width of W is sublinear in L. So if you can prove the hardness of this assumption from LWE for anything that's sublinear in L, so it doesn't have to be all the way to just poly n log Q, you would already get non-trivial things like broadcast encryption. Okay?
So the syntactic question, just
yes.
terminology. So the things that Kotek was talking, he used a different word. I think he used like evasive.
Evasive LWE.
So is there any relationship on the
The evasive LWE is a different assumption. Yeah, maybe that's the easiest way to put it. So evasive LWE is a much more complex lattice assumption.
So it's unrelated currently?
This is a weaker assumption in the sense that evasive LWE, in fact, the weakest form of evasive LWE, public coin evasive LWE, implies all assumptions in this family.
Always.
Yeah, and this is a falsifiable assumption. Evasive LWE is a non-falsifiable assumption. Yes. Mm-hmm. Yeah, so here I can actually give challenges. I can give parameters. I can, it's a much simpler from a cryptanalysis perspective. Good, okay, so that's one axis of hardness. Another axis that we can consider is what happens as the dimension L increases, right? So here again, when L equals 1, right, when this matrix is just, I give you a trapdoor for A with W1 and assume W1 is at least has width n log Q, then this again follows from the LWE assumption. This is again standard trapdoor extension techniques. And one might think that as I make L bigger and bigger, I'm giving out a bigger and bigger trapdoor, the assumption should get easier and easier and easier. It turns out, though, that in this particular case, that's not quite true. That in the sense that once I have L to be roughly 2m squared, where again, remember, m is just the width of A, this actually implies the assumption for all larger L. Another way that you can think about this is if I give you this trapdoor for L equals 2m squared, I can actually simulate a trapdoor for any larger value of L. Okay? Actually, in fact, using the techniques that I'll be describing later on in this talk. So that's sort of unlike Q-type assumptions in pairings, right? In pairing-based cryptography, it's usually not the case that an instance of the assumption of size q implies the assumption for a larger instance size. Here it's saying that once you get to 2m squared, which is, remember, polynomial in the security parameter, independent of other things, this is, it implies all larger instances of the problem.
The other way also goes, right? Like L implies L minus 1.
Yes. The other way also goes. Yes, exactly. Yep. So if you want a concrete instance, this is the only one you need to understand. Then you get all other instances. Okay, great. So over the last couple of years, we've now accumulated quite a few examples of applications of succinct and decomposed LWE. Typically, these assumptions so far has been useful for compressing things, for improving the rate of cryptography. So getting things like optimal broadcast encryption, nearly optimal key policy or ciphertext policy attribute-based encryption, fully succinct randomized encodings, which I think Julio will talk about later in this workshop. All of these are the kinds of things that you can build from this family of assumptions. Okay, and a very exciting development that we'll actually hear about, I think, in 3 weeks is in an upcoming work, Kotek actually showed that using the techniques that were inspired by sort of this line of work, we can actually now get functional commitments for circuits and snarks for Boolean circuits just from the plain SIS assumption. Hopefully this gives some credibility that by studying constructions along these lines, we can ultimately achieve the goal of basing them on standard assumptions. So far, it doesn't seem like these techniques apply to the other primitives listed on this slide, but maybe next year we'll have made some more progress. Okay. All right, so what's the general roadmap for the remainder of my talk is going to be as follows. I've now described for you this general family of assumptions, and I'm not going to focus on any particular instance. Any instance within this family will suffice for everything that follows. And now I'm going to describe how to use this to build new kinds of cryptography. And the way that I'm going to do so is I'm going to first introduce this abstraction called a matrix commitment scheme. And it turns out that using succinct LWE, you can realize this notion called a matrix commitment. And a matrix commitment is actually the object that is very useful for realizing a broad range of cryptographic applications. And I'm going to focus on 2 main applications to distributed broadcast encryption, as well as key policy and key policy ABE with succinct ciphertexts. Yeah?
Just to check, when you say the succinct LWE family of assumptions here, you mean like succinct LWE and decomposed and
any of them.
All of these ones that we've talked about?
Yes, all of the 3 that I listed that are in this family can be used to instantiate the matrix commitment, which in turn gives you all of these applications. Yeah, so it's actually, in my view, easier to think about the matrix commitment object rather than try and do it directly from succinct LWE. Yeah, so in the first part of this talk, I'm going to focus on matrix commitments and how to use them. And then in the last part of the talk, I'll show you how this implication goes. Okay, so here's a very useful abstraction. It's a notion of a matrix commitment, which at a very high level just consists of 2 algorithms, a commit algorithm and an opening algorithm. And it basically gives us a way to commit to a very long matrix M. So you should think about M as n by L, where L is very large, right? L could even be exponential in the security parameter. So L is a big matrix, is a very, very wide matrix. And there's a commitment algorithm that basically takes this very wide matrix and compresses it down into a short matrix, into something that's very narrow, just M by M, where we call M is n log Q. M is independent of L, okay? And then there's an opening algorithm that outputs a long matrix, M by L. So the key equation that a matrix commitment scheme should satisfy is the following equation. It says that if I take this commitment C, and I multiply it by what I'll call an expansion matrix, right, this V sub L. This V sub L is a matrix that's determined completely by the public parameters. It basically expands C into the matrix M that I committed to, minus some translation, where the translation is A times the opening Z, okay? The main properties we want are as follows. First, the expansion matrix V and the opening Z, these are low norm entries. The entries in these matrices are small. And moreover, the matrix A and the expansion matrix V, these are completely determined by the public parameters. The commitment, the matrix M, and the opening otherwise are the quantities listed above. Yes?
I don't understand. First, the opening takes C as an input, not M, correct?
No, it takes M. So it takes the matrix M that you're opening to. So these are deterministic algorithms. Yeah, so the opening algorithm could compute C if it wants, but it doesn't need to. Like M completely determines C.
Commit is deterministic.
Both of them are deterministic.
Oh, okay.
Yeah, I haven't defined any security properties. Right? I'm purely defining a correctness requirement.
So what is how do you define commit? How is C built?
We'll see. Yeah, so right now I'm just describing the syntax. I haven't told you how to build this object. That's at the end of the talk.
Z.
I'm just describing syntax right now.
What is Z? Is it derived from the public parameters?
Z is an opening, so it's derived from the public parameters and the matrix M that you committed to. So there's an opening algorithm that takes the parameters, takes M, and outputs Z. And outputs a Z that satisfies this equation. Yeah?
When you say determined by the public parameters, should I just think of them as being like actually public parameters but somehow like compressed?
You can even think about the public parameters right now as just being the description of the matrix V and the description of the matrix A. Yeah, there will be a compressed representation later, but it's perfectly fine to just think about them as the actual matrices themselves. Okay? So far, so good? So this is the key equation. This will give us almost all the applications we care about. Okay. Okay, I guess the answer to Yoon's question. The public parameters, it turns out, in the actual construction, will be a uniform random string, and technically it's actually going to be short. It actually only depends on logarithmically in the dimension, but for now you can even think about it as I give out the public parameters that just tells you what the matrix VL is and what the matrix A is. That's also fine. Yeah, but it turns out that this will be short. Okay, and now I have a security property. The security property that we want is that LWE holds with respect to this matrix A, even if I give you the public parameters for this commitment scheme. Okay, so I give you the public parameters that allows me to define the commitment and the opening algorithms. The commitment and opening algorithms allows me to sample M and Z, C and Z that satisfies this equation, and I want LWE to hold with respect to the matrix A. Okay, so I haven't told you how to build this object yet. I will show you how to build this object at the end of this talk. So right now I'm just describing the abstraction. Yes?
So commitments, we know what the definition and syntax is. You commit to something, and the security property is that you cannot open it into two different ways. So here you're giving a security property that is on top of that. You have a sort of, it's not just a commitment scheme where the message is a matrix. You have some...
You have some pseudo-randomness property as well.
Commitment scheme with some special property, but the special property is defined in terms of LWE. It's not like an abstract property.
Correct. Yes, this is an algebraic commitment scheme. Yes, it's an algebraic scheme where the security property is an LWE assumption. Yes. Yep, the algebraic structure will actually be useful for the applications. Okay, so let me try to show you how we can use this. So the first application I'm going to tell you about is this notion called distributed broadcast encryption, which is basically the question of how do you encrypt to a public key directory. So so the setting is as follows. We have a collection of users, and they generate public keys independently. So just imagine they're using a vanilla public key encryption scheme. They generate their public keys, and they post their public keys to some public key directory. And suppose at some later point in time, I want to encrypt a message to some arbitrary subset of these users. Right? Maybe I want to encrypt a message to Alice and Carol. The naive way of doing it, or the standard way of doing it with vanilla public key encryption, is I can separately encrypt to Alice's public key and Carol's public key and send the ciphertext to Alice and Carol. This will lead to a construction where the size of the ciphertext grows linearly with the number of users in this broadcast set. And the goal of distributed broadcast encryption is to be able to encrypt to an arbitrary set of public keys with a single short ciphertext, something that scales sublinearly in the number of recipients. So more formally, the syntax of a distributed broadcast encryption is as follows. There's a setup algorithm that generates a set of public parameters for the scheme. Then every user can run key generation that basically samples a public key and a secret key. Notice that there are no master secret keys in the system. There are no, everyone generates their keys individually and independently of everybody else. Then you can encrypt. So the encryption algorithm takes a set of public keys that you want to encrypt to, together with the message, and produces a ciphertext. And the efficiency requirement is that the size of the ciphertext should scale sublinearly in the size of the set. In fact, here, polylogarithmically in the number of users. And finally, the decryption algorithm will basically take the set of public keys, take a secret key, and take a ciphertext. If you have a secret key for somebody in the set, you should be able to decrypt. And if you do not have a secret key for somebody in the set, the message should be computationally hidden. So this is a trustless version of the notion of broadcast encryption, originally introduced by Fiat and Nauer, where there is no central authority. Everybody chooses their own public keys, samples them independently of everybody else. Notice that this does imply broadcast encryption, where there's a polynomial number of users and a long master public key. You can just define the public parameters for your centralized broadcast encryption as the concatenation of the public keys that you sample. And in fact, if you don't want that the encryption algorithm and decryption algorithm have to know the exact public keys, if you just want them to know the identities, it turns out that you can handle this notion as well. This is what I'll call a registered version of the primitive. I won't get into too many details there. But you can get the more generalized notion if you want. OK, so let me show you how we can build distributed broadcast encryption via matrix commitments. The entire construction fits in one slide. So here I have the key equation for the matrix commitment scheme. So the public parameters for this scheme will consist of the public parameters for this matrix commitment scheme. It will consist of a random matrix A0 and a random vector P. Okay, this will be used to implement a dual regf style of encryption. The key generation algorithm just samples a random binary string of dimension m. The public key for each user is going to be derived by taking A times the secret key plus this public P minus A0 times VI, where VI is basically the ith column of this expansion matrix here. Okay, so I'm going to parse this expansion matrix V as basically the concatenation of V1, V2, blah, blah, blah. Right? The key for a user I, where I is the identity, will just be a linear function defined as such. The secret key will just be Ri.
What is A?
A is the matrix in the matrix commitment, determined by the public parameters. Yep. OK, so the question is how to encrypt. So imagine that I want to encrypt to a collection of public keys. What is the structure of the public key? The public key is just a vector. It's an n-dimensional vector. So what I'm going to do is I'm going to construct a very sparse matrix where in the ith column, if the user I is in the set, in the broadcast set, then I put user I's public key there. If user I is not in the set, I put a 0 column there. Okay, so now I have this sparse matrix where the number of non-zero columns is exactly equal to the size of the broadcast set. And now I simply commit to it. Okay, so I just commit to this matrix. At this point, I have all the ingredients needed to encrypt. I sample my LWE secret, and now I craft an LWE encryption. What does that look like? Well, S times A plus E, that's the LWE part. And S times P, this is sort of the dual regf encryption of the message. And then in the center here, I have the set. I basically have the thing that pertains to the set. So I basically give out an LWE instance with respect to A0 plus the commitment to all of the public keys. So you can also think about this construction as I take all of the public keys in my broadcast set, and essentially I hash them. What is the hash function? Well, I basically commit to all of those public keys. And then I give out an LWE instance with respect to that committed public key. OK. Sorry? C? C is the commitment. P is part of the public parameters. Yeah. Yeah, so you can think about the first row and the last row as a dual regf encryption of the message mu. OK, so this is the entire construction. Let's take a look at how we can decrypt. How do we get correctness? So correctness will rely on this opening relation. So suppose I'm an element in the set, right? I'm a user that is being broadcast to. What does that mean? That means I can take this commitment. Remember, this commitment is to all of the user's public keys. And I can multiply by the ith column of this expansion matrix. What does the ith column of the expansion matrix do? Well, it maps the commitment C to the ith column of the commitment. What is that? Well, by definition, that was the ith user's public key. So I get exactly T sub I minus A times the ith column of the opening, right? Now, what is T sub I? Well, that's exactly how I defined it here. It's just A times Ri plus P minus A0 Vi, and then minus A times the opening. So at this point, I claim that we're basically done. Why are we done? Let's consider the decryption process. I take the second component of the ciphertext, multiply it by V sub I. And if I just expand things out, I basically get S times A0 times Vi plus S times C times Vi, but we know what C times Vi is. So the key observation here is that this A0 Vi term cancels out, right? This disappears, and I'm left with S times A times something short plus S times P. So Ri is known to the user. That was the user's secret key. Zi is the opening. That's publicly computable. And so the user can take the first component of the ciphertext, multiply it by the difference Ri minus Zi. That gives me this term. And now I simply subtract and recover S times P. And now I can decrypt. Okay? So if you're an element in the set, you can directly decrypt. You compute the opening for your to the committed set of public keys, and that allows you to recover the blinding term and decrypt the ciphertext. Okay, so immediately this gives us a selectively secure distributed broadcast encryption scheme. I won't go over the security proof. It's basically two hybrids. It's actually quite simple, but in the interest of time, I won't do it. Yeah?
When you think about trying to compare this with BGW, it seems like structurally there are a lot of similarities. Is there a way to write down pairing-based construction using some type of a pairing-based matrix commitment, or not exactly matrix commitment?
It's a good question. I don't think this is quite BGW-esque because the security proof follows a very different structure. But,
yeah, security proof does follow, but let's just abstract out core component of. There is basically a vector commitment hidden in BGW, in a sense.
Yes.
The matrix commitment kind of looks very similar to that. So the proof from that type of an abstracted vector commitment pairings would look kind of like very similar to that. It's like I understand that there is kind of like reggae happening here. Over there, you'll sort of just kind of like do kind of like a pairing-based argument.
Kind of. The analogy is not quite as direct, but yeah, it is somewhat close. Yeah, there's some. Yeah. So you can sort of extract a pairing-esque construction from this as well. But yeah, we can talk about it more offline. Yeah. So previously, such a scheme was only known from witness encryption or I/O. So now we give one from any of this succinct LWE family of assumptions. I'll say a few generalizations. We can, for instance, prove adaptive security in a random oracle model. We can also we can generalize this to get registered attribute-based encryption, so trustless version of attribute-based encryption that supports an unbounded number of users and has succinct ciphertexts also in a random oracle model. And this is also something that's not known from. In fact, this latter implication is not known from witness encryption.
Is it broken if A0 is not there?
Oh, good. Yeah, so what is the purpose of A0? So that's a great question. In fact, nothing in this correctness did not depend on this A0. The A0 is only needed to facilitate the selective security proof. I don't think there's an attack without A0, but I also don't know how to prove security. Yeah, A0 is basically used to program the set. So if you're imagining a partitioning type proof strategy, A0 is basically used to program the challenge set into the challenge ciphertext. Okay, good. So let me show you one more application. So this time to attribute-based encryption. So what is attribute-based encryption? Here I'm going to be in a centralized setting. So there's a setup algorithm, generates a public key and a secret key. In key policy attribute-based encryption, there's a key generation algorithm that takes the secret key and the function f and outputs a secret key for the function. Then there's an encryption algorithm that takes an attribute x, a message m, and produces a ciphertext. And the correctness requirement is that when I decrypt, if the attribute satisfies the policy, then decryption succeeds. So in this case, we say f of x equals 0 means decryption succeeds, and f of x equals 1 means the policy is not satisfied and decryption fails. When we talk about a succinct attribute-based encryption scheme, the property we want is that the size of the ciphertext does not depend on the size of the attribute. Right? So the length of the ciphertext only depends on the length of the message, plus something that is only polylogarithmic in the attribute size. In fact, in the following, I'm going to cheat a little bit for reasons that often comes up in lattices. I will allow a depth dependence in the size of the ciphertext. So it will depend on the depth of the Boolean circuit that computes the policy. OK, so to build attribute-based encryption, I need one more piece of machinery. So this notion of homomorphic computation using lattices were introduced first in the work of Gentry, Sahai, and Waters, and refined in the work of Bonnet et al. And the idea here is basically there's an approach that allows me to embed an input x into a matrix, right? So the way that we embed it is as follows. We have a very wide matrix. So I want to embed an attribute of length L. I'm going to have a matrix that consists of L blocks. And I'm simply going to shift the ith block by the gadget matrix if xi equals 1. Otherwise, it's just bi, right? So you can view b minus x tensor g, this object here, as an encoding of x with respect to the matrix B. And the homomorphic evaluation machinery basically says, given any function f, there exists a low-norm homomorphic evaluation matrix H that basically transforms an encoding of x with respect to B to an encoding of f of x with respect to the matrix B sub f. Okay, so this is the only property we need from homomorphic evaluation. And finally, given the matrix B and the function f, there's an efficient algorithm for computing this matrix B sub f. Okay, so let me now recall for you the Bonnet et al. Attribute-based encryption scheme from Lattices. So again, this is a fairly simple construction nowadays. So the public key consists of a dual rega public key, so random matrix A, random vector P, and then it has this attribute encoding matrix B, right? This will be used to encode the attribute. The secret key will be a low norm vector that recodes from A concatenated with B sub f. So the secret key depends on the function f. It basically recodes from A concatenated with B sub f to P. And the ciphertext now has the following structure. I sample my LWE secret, and I give out dual reg f encryption of the message, so S times A, S times P plus the message. And then in the middle, I have the attribute embedding component. So B minus X tensor G, this is the encoding of the attribute. So I give out an LWE instance with respect to the embedded attribute. So how do I decrypt? So let's look at the decryption relation. What we'll do is we'll take this guy and we'll multiply by the homomorphic evaluation matrix. The property of the homomorphic evaluation is it translates an encoding of X to an encoding of f of X. In this case, I have an encoding of X multiplied by H will give me an encoding of f of X, where minus S times f of X times G. But when the policy is satisfied, f of X equals 0, this term vanishes. So I just get S times B sub f. So at this point, hopefully things are pretty standard. I can take the first term and this term. I compute S times A, S times B sub f, multiply by this recoding term. This gives me S times P. Once I get S times P, I am done. Oops. All right, I can now recover the message. Okay, so in this particular construction, the ciphertexts are not succinct, because if you look at the size of the ciphertext, it grows linearly with the length of the attribute, right? I'm embedding the X, the attribute X, into the matrix B itself. So the size of this attribute scales linearly with L. So this is not a succinct attribute-based encryption scheme. So how do we make it succinct? The approach is to replace the long matrix, the very wide matrix, with a short one. How do we take something long and make it short? We commit to it, right? We hash it, right? So we're going to compress, in this case, the encoding of X, so X tensor G. So how do we do that? Let's commit. So let's say C of X is a commitment to X tensor G. What does the commitment relation now say? It says that if I take C sub X, I multiply by this expansion matrix, I get X times X tensor G minus A times the opening. Okay? So now what I'm going to do is I'm going to compress B, right? I also need to somehow compress B. The way I'm going to do that is I'm going to define B now as B tilde times the expansion matrix, right? I'm going to define B tilde to be a random n by m matrix. And then B will just be B tilde times V. Okay? So this long matrix here has now been decomposed and written in this form, B tilde times this V matrix. So at this point, the key observation is that B minus X tensor G, so this long component in encoding here, this can be written as B tilde times V from here, minus the commitment times the expansion matrix, minus A times the opening from the matrix commitment relation. At this point, I claim that we are done. What we will do to get a succinct attribute-based encryption scheme is we replace the attribute encoding matrix with its compressed representation as B tilde. And in the ciphertext, instead of encoding the attribute, we will replace it with an encoding of the commitment to the attribute, which is short, right? And how do we see that this works? Well, observe that if I take this guy, multiply it by the opening, and I take this guy and multiply it by the expansion matrix V, what do I get? I get exactly this expression here, which is exactly the original Bonnet et al. Encoding of the matrix M, X, right? So essentially, you can view this as a way to compress the Bonnet et al. Encoding of the attribute X in the ciphertext, as well as in the public parameters. Everything else is unchanged. So we just replace X tensor G in the ciphertext with a commitment to X tensor G, and that gives us compression.
And what is the assumption now?
Any of the succinct LWE family of assumptions.
Pardon?
Any of the succinct LWE family of assumptions. Yep, so anything that gives you matrix commitments, which is a succinct LWE. Okay, any questions? All right, so the only thing that remains is to show you how to build this matrix commitment object. So hopefully I convinced you that this is a useful abstraction. Once you have a matrix commitment, you get applications almost for free. Okay, so let's see how to construct this. It turns out that this is actually not too difficult to construct. we're going to use the succinct LWE trapdoor to construct this object. So recall the succinct LWE assumption basically says that I give you a trapdoor for the structured matrix D sub L. Okay? The matrix A along the diagonal concatenated with a vertical stacking of all of the WIs. So as a warm-up, I'm going to commit to something of a simpler form. I'm going to commit to something of the form X tensor G. In fact, if you recall the application to attribute-based encryption, it was already sufficient to just commit to X tensor G. Okay, so all I'm going to do is I'm going to just write down the succinct LWE trapdoor. Right? This is the succinct LWE relation that we have. And I'm going to multiply both sides of the equation by X tensor I. What is X tensor I? It's basically a block matrix where each block is Xi times the identity. So let's see, what does the left-hand side become? The left-hand side becomes X1 times A, X2 times A, and so on. That gets you that part. And then it gets you basically the linear combination of the W1s up to WLs scaled by the Xi, the sum of Xi Wi. What happens on the right? Well, because I have blocks that are at the identity, I get X1 times G, X2 times G, and so on. So I get G basically scaled by the bits of X, which is exactly X tensor G. So I almost have something that looks correct. In fact, I actually do have everything that I need. Okay? So this is the new expression. Now let's just expand. Right? Let's just compute the matrix vector product. This can be written as the sum of Xi times A times Ti. Because the Xi's are scalars, they commute. Right? So we can write this as A times the sum of the Xi times Ti's plus the last block, which is the sum of Xi Wi times T-bot. So once we have this, I claim that we actually already have something of this form. Why? Let's just rearrange things. I'm going to move this thing to here. And now I have something times T-bot is equal to X tensor G minus A times something. Right? So all I will do is I will call the thing on the left the commitment, the thing on the right the opening, and then the expansion matrix is the last block of this trapdoor, and that's it. Okay? And the only remaining thing we have to check is that V sub L, the expansion matrix, and the opening are low norm. But notice how they were constructed. They were constructed by taking blocks of the succinct LWE trapdoor. So by nature, they have low norm. So we are done. Okay, so this is a deterministic object. The commitment is just you take a linear combination of the blocks of the W's. The openings is you take a linear combination of the blocks of the trapdoor. Okay, but I will promise you to commit to a matrix. Right? Here I've committed to X tensor G. How do I commit to a matrix? We use this magical property, this compactification lemma from a work of Brzezinski, Zabary, Vaikunthanathan, and Wee, where they basically showed that you can actually decompose a matrix M as a product of basically the binary decomposition of M multiplied by some rearrangement of the identity matrix. Right? So I'm not going to prove this lemma. This was proven in prior work. Basically, this is a simple equation of one way that you can decompose the matrix M. Okay, and just in word annotation, the vectorization, so vec here is the vectorization, it basically denotes the vector obtained by concatenating all of the columns of the matrix. And bits of M just means take the binary decomposition, so compute G inverse of M, and then take all of its columns and concatenate them together. Okay, so the only observation we need is that this component here is basically just blocks consisting of the identity matrix. This matrix, by definition, has low norm. So if I want to commit to a matrix M, what do? Well, I'm going to use the fact that I know how to commit to something of the form X tensor G, where X is now the binary decomposition of M. Right? So this is exactly the same opening relation as above. And I simply multiply both sides of this equation by the blocks of the identity matrix. Right? And I claim that this is actually something of the required form. How do we see that? Well, if we just look on the left-hand side, we have something of the form C times the expansion times a low norm thing. This is still a low norm thing. I just define my new expansion matrix as the trapdoor times this blocks of the identity matrix. So I get C times VL. Here, by the compactification lemma, that's exactly the the matrix M. And finally, the opening is already of the form A times short. So this remains low norm, and I get the commitment to an arbitrary matrix M. Okay, so just to recap, once I have the succinct LWE trapdoor, I immediately derive a matrix commitment from first principles. Okay, so the one last thing that I'll mention, and then I'll wrap up, is so far, as I defined it, in order to commit to a matrix M, I need a very long trapdoor. I need a trapdoor that's basically as wide as the matrix M. In fact, even wider, L times M. What if I want to commit to something using a fixed size trapdoor? Turns out that you can actually commit to a long matrix using a trapdoor of dimension only 2m squared that's independent of L, essentially by using Merkle-style recursion. And the way to show that is I'll just show by example. Suppose I want to commit to a matrix of dimension 4m, right? Where I have a matrix commitment scheme that works for matrices of dimension 2m. What can I do? Well, I can take my matrix of width 4m, chop it into 2 blocks, a matrix each of width 2m. I can commit to each of those 2 blocks. The commitment basically does compression from 2m to m. So now I have a new matrix that's n by 2m. So I got a 2-to-1 reduction. And then what do? I commit to the commitment. And that produces a final commitment of dimension m by m. Right? So you can think about this matrix commitment on dimension 2m as basically implementing a 2-to-1 hash function. Right? And then you can just recurse using standard Merkle. So if you want to view correctness, maybe I'll skip this, but it's actually not too hard to see. If you just write out the commitment relations, you have C0 as a commitment to M0, C1 is a commitment to M1, C is a commitment to C0 concatenated with C1. So how do you open C to M0 and M1? Well, what you would do is you want to multiply C0 by this opening, C1 by this expansion matrix. That would give you M0 and M1. So you just do exactly that. And then you write everything out, and you get exactly C times this thing here gives me M0 concatenated with M1 minus a new opening. So this is the recursive structure. OK. And of course, this generalizes much more than just matrices of size 4m. OK, so we get a Merkle size commitment where now the public parameter size is independent of the length of the matrices that I'm committing to. We can, in fact, even, because it's a Merkle-style construction, we can even commit to sparse matrices of exponential width. So this was actually useful when we talked about broadcast encryption for an arbitrary number of users. As long as the matrix M only has polynomially many non-zero columns. And then you can realize this from any assumption in the succinct LWE family. The way you do that is the public parameters for the commitment scheme is exactly the public matrix together with the trapdoor from the succinct LWE assumption. And if you instantiate this with decomposed LWE, notice the appealing property of decomposed LWE is that this matrix T was actually public. You actually get a scheme where the public parameters can actually be sampled in a transparent manner. It just consists of a uniform random string. Okay? And then the succinct LWE assumption basically asserts that SIS or LWE holds with respect to A given this matrix D and T, but that's exactly the public parameters. So the succinct LWE assumption exactly gives you the security property of the matrix commitment scheme. These are equivalent. Okay, so just to summarize, in this talk, I've introduced this notion of the succinct LWE assumption family. And we can instantiate assumptions in this template that follow this template from several assumptions that have been recently proposed, such as basis, succinct LWE, and decomposed LWE. All of them can be used to realize something in this general family of assumptions. And in particular, when it comes to building constructions, this object, this matrix commitment object that follows immediately from any assumption in this family seems to be a very useful building block. It gives us nearly optimal ABE, it gives us distributed broadcast, gives us succinct registered ABE, and more. Yeah?
Is there at this point anything that you need, like, let's say, the stronger assumptions, like basis for, that you don't know how to do from decomposable? Or?
Nope. You get better parameters. So because the stronger the assumption, the more succinct things get. But you can shave off, let's say, polynomial factors. Yeah, but all of the assumptions you can get from decomposed LWE, and it does have a polynomial blowup in the parameter size, but that's the only payout cost. Yeah?
Is it possible to like equivocate the matrix commitment, like open to like a random Gaussian pre-image set?
Yes, so there's that. Yes, so you can also, using the trapdoor, you can actually sample a random commitment and opening that satisfies the relation. Yes, that's also possible. Yeah, that's actually useful for the registered ABE application. We actually need sort of this samplability property. Yep. Okay. So let me leave you with a couple open problems. So I think the most interesting and the most relevant open problem is, can we say anything more about the hardness of these new lattice assumptions? And in particular, what would be really nice is if we can show, let's say, the hardness of decomposed LWE from plain LWE. That would immediately give all of the, give a construction for all of the various primitives I described in this talk. An intermediate goal might be to find some kind of worst case lattice assumption and show that that implies decomposed LWE. I think that would be very interesting as well. I think certainly we need more cryptanalysis. This is a new family of lattice assumptions. Can we understand hardness better? Can we find non-trivial ways of using sort of this trapdoor to help break the assumption? And finally, what are the other kinds of primitives that we can build from succinct LWE? So I guess ordered in roughly in what I think is an order of difficulty. So I think something that seems within reach is something like a succinct computational secret sharing scheme. Again, it's a property where we want succinctness. It would not surprise me if we can do that from something in the succinct LWE family, and then building up to witness encryption or even obfuscation from this assumption. Thanks.
What's succinct computational secret sharing?
Good. So imagine that normal computational secret sharing, you want to secret share a message to n parties with respect to some policy, and you want the total share size to be sublinear in, let's say, the size of the policy. So Shamir secret sharing would be, yeah, for general policies. Yeah, so Shamir secret sharing is succinct for threshold policies, but for general policies, yeah, I think we need I/O, basically. Yep. Great.
Questions? I guess that's the thing.
Cool. Thanks.